So I'm going to talk about inference. From more or less a quantum field theory point of view, I'm going to attempt to make it very accessible. And I think one of the real problems for physics is that quantum field theory is not accessible enough. So I've spent the last 20 years focused on renormalization, but I'm not going to talk about that at all. There are three recent articles that talk about, I'm going to have to speed up, that talk about the relationship between quantum mechanics and classical mechanics and about the measurement problem. But they do so in terms of an underlying ideas about quantum field theory, and specifically as if it's a noisy signal analysis formalism. And I think that can make contact with this workshop in the sense that inference and machine learning can be thought of as data analysis toolboxes. So one can approach the relationship between quantum mechanics and classical mechanics in so many different ways. The way I've chosen to do for the last few years is partly through the idea that no-go theorems tell us that quantum mechanics is more than, in some sense, classical mechanics. And so one approach following on from that is to think that we should try to construct a more complete version of classical mechanics, add to it, instead of trying to add to quantum mechanics so that it's more like classical mechanics. And in the articles above, I construct what I call CM+, and that includes in the first instance measurement incompatibility. So in algebraic terms, non-commutativity. You can use the Poisson bracket. If you're willing to use it in its full power, you can use the Poisson bracket to construct a full algebra, a non-commutative algebra of measurement operators, measurement observables within classical mechanics. It's been strawmanned. Classical mechanics has been strawmanned so that you cannot use these things just by fiat. If you do this, then the next thing you need to do is to introduce the idea, well, is to recognize that quantum noise and thermal noise cannot be the same thing within this new structure. You need to find some really solid difference. And quantum field theory actually has a solid difference. Quantum noise within quantum field theory can be thought of as just the Lorentz invariant component. The vacuum is Lorentz invariant, and so its noise, insofar as you're willing to accept that there's noise there, is Lorentz invariant. And that, for me, as a field theorist, implies that we should really think of CM+ as a field theory. So a random field theory would be a terminology that can be used. But I'm not going to include into this analyticity, what I'm going to call analyticity, which is a consequence of the fact that quantum mechanics projects to positive frequencies, which CM+ does not. And I want to keep them separate because I want to be able to compare CM+ with quantum mechanics, quantum field theory, and see what the differences are, and hence perhaps learn something about both. And indeed, this projection of positive frequency is very similar to what you find in signal analysis, where there is the idea of an analytic signal and a real signal, essentially as the positive frequency and the not positive, and an unconstrained frequency. Okay, so CM+ is a Hilbert space formalism for noisy signal analysis. And insofar as it is a Hilbert space formalism, it can describe experiments equally well as quantum field theory. And indeed, for the electromagnetic field in particular, not for all such things, we can construct isomorphisms, linear isomorphisms between quantum electromagnetism and what I call CM+ electromagnetism. So this is not quantization because it is isomorphisms. It's a much cleaner construction. It's not a replacement for quantization, but it is an alternative that I suggest is useful to have in the toolbox. It's not a panacea. It's statistically non-local. This is something that is going to have consequences down the road as we try to study what it might do. Okay, so I submitted this abstract to Priya 5 weeks ago, and I've struggled to keep to it. Correlation is not equal to causality, obviously a very naive sort of thing. What do we have to add to it? Causal modeling does add something to it. Intervention in particular gives us a means of talking about causality. In mathematics and physics, however, we have generalized probability and contextuality, which gives us similar tools in a framework that is essentially algebraic as a whole, and in that sense, I feel that it's more unified. Obviously, this is to people's taste to some extent. And for machine learning, we'll discover in the last 4 slides whether or not I have something interesting to say. So Again, there are so many things you can pick out from causal modeling. The do notation, so many people pick out that, well, of course I should as well. In any case, it seems connected to the state preparation that one has in quantum mechanics. So we have required for a transformation is more or less you take a dial, you turn it to x, there is your, I have willed it so. You could have turned it to x1, x2, x3, you didn't, you turned it to x. So do x equals x is semantically different in that sense from it happened that x equals x. You made no, there was no will involved at all, but mathematically it's just the same. Both of these constructions can fit perfectly well into as models of the Kolmogorov axioms. So we have experimental protocols decree what will be done by the experimenter. The experimenter typically is not free. There is a design of the experiment that says you will choose random numbers. If you choose all zeros, then you will have to do the experiment again. We can transform any aspect of an experimental apparatus by having enough dials, each one of which is connected to the internals of the apparatus so that things happen. And afterwards, however, there's just data in computer memory. That is what you're going to use. You're going to apply any algorithm that works. And you've done multiple interventions, and you keep track of what interventions you've done to obtain that data. So from a data analysis perspective, one thing we obviously do is construct relative frequencies. And for that, we just construct a number between 0 and 1, but a rational number. And we can add those, as long as we don't double count, to get a new relative frequency. We can add many of them, so long as we don't double count or omit anything, we'll get the number 1. And, well, we have to keep track of double counting and omission in one way or another. So historically, the relative frequencies came out of the 19th century. The Kolmogorov axioms followed that mathematics, and if it hadn't, we'd be talking about someone else's axioms, I suggest. And then, once we have the Kolmogorov axioms, then we can construct models for those in terms of expected values for the relative frequencies, which are now real numbers instead of rational numbers, perhaps. We can talk about different semantics, so something like propensities. We can talk about the do semantics. And we can also construct linear algebraic models for the Kolmogorov axioms. So when we construct a... nope, wrong thing. I've just gone forward a line that I didn't intend to, but I won't go back. So when we construct relative frequencies, then we hope that those will turn out to be the same as what we had from a theory that we had written down. Algebraically, we could use compatible, so commutative operators, to construct this. Also gives us a positive number, and so by choosing the right state and the right projection operators, we can make this be the same as this. But also, we can, if we want to, use arbitrary, so long as the spectrum of the operator, no, arbitrary operators at y and x, that give us the same numbers as this, but using non-commutative operators. And this, in fact, is the mathematics of the collapse of the wave function, but just used to construct a conditional probability, or indeed at the top line, just joint probability. So we have generalized probability gives us ways to interpolate between different contexts. So if we do find many relative frequencies, and we find in many different contexts, we place a new context relative to an earlier context, then we can compute expected values for the new relative frequencies. And that's what we get out of the linear algebra of quantum mechanics in particular. Incompatibility is a way of placing contexts as non-trivial transformations of other contexts. For quantum mechanics, we can do that straightforwardly because we can generate transformations instantly just by using any omission operator. For CM+, it's a little more difficult because we only have a commutative algebra, but we can use the Poisson bracket to construct the transformation algebra, Dirac's transformation algebra. And that then we can use, so long as we don't straw man ourselves, to construct just the same algebra as we have from quantum mechanics or quantum field theory, in fact. So I'm going to talk about the Bell inequalities, with apologies, but entirely from a field theoretic point of view. This is an experiment from the 1995. This is page 60 from Gregor Wies's thesis. It's a really nice diagram from my point of view, partly because up here, I do have to go back from now on. Up here, he talks about a pump. He pumps the electromagnetic field, as I will say. He doesn't shovel particles in. He pumps the electromagnetic field. Then he also is extremely clear about what he's going to store. He's going to store the time at which events happen. No particles in this at all, in this description. It's not that you can't have a particle description, but if you do, then you're going to have quite a compromised idea of a particle in order to do so. But from a field theory point of view, the idea of pumping a noisy field, it's actually perfectly straightforward for me. So he also, again with the wrong key. So he also stores which of these avalanche photodiodes actually had the signal went from some low end. I have a beautifully shaky hand, which is exactly as shaky as the display there. And when an event happens, then that's the time which Gregor stores. And at the same time, he also stores the random bit generated value that has set the electro-optic modulator here, which is changing the polarization on a sort of megahertz scale so that we can say something about causality. It needs to be that fast in order for this to be a good test of that. On the other hand, this experiment is much simpler than the 2016 experiments, and so I don't want to use that for display. So here's the actual data. My computation of this. This is 15,000 events. Oh, again, 15,000 events, and you can see the coincidence there. Within about 1 nanosecond, all of these 15,000 events total across all of these plus or minus 3 nanoseconds. And indeed, you can see that many of the events are green and yellow in the color scheme I've used here, where the red is the diagonal, the blue is the lower diagonal, and the yellow and the green are the other 2 diagonals. And that green and yellow is actually signifies the violation of other inequalities. If you turn that diagram on its side, you slice it 100 times in this way, you can compute a histogram that counts each of the 16 different types of events. You can add up those numbers, and then you can put that into, by now, a completely standard calculation of a violation of Abelian inequalities. So all we've done here is we have a completely classical set of data. We've applied a completely classical algorithm, and out of that we've got a number at which point classical particle physics says, no, this is not any good. We cannot have this. So what I'm going to point to you is that in quantum mechanics, we actually use measurement incompatibility, the non-commutativity of the algebra of the measurements, to model the violation of Abelian inequalities. And this is something you find in the literature since about 1980. In classical mechanics, as usual, we don't have measurement incompatibility. We strawmanned ourselves, so we're not allowed to do it. One response to this is, well, you can read what comes next as well, is we can say that classical mechanics is computationally incomplete. Quantum mechanics is more than classical mechanics. So we can use the Poisson bracket to add measurement incompatibility into classical mechanics, giving us CM+, so it's computationally as complete as quantum field theory. It's just a more effective thing than classical mechanics itself. So I've focused on non-commutativity. There's clearly a whole pile of literature about non-locality. For quantum fields, microcausality asserts that locality is closely associated with measurement incompatibility. And indeed, there's a version of that which is called Hague duality, which really makes it identical. Quantum fields are, however, are much less like classical particle physics than they are like the heat equation or any kind of non-equilibrium thermodynamics. So those kinds of things do depend on the boundary conditions. Once you set the boundary conditions, the whole system will equilibrate to the boundary conditions. So completely different from what one expects for a particle physics intuition. And indeed, temperature measurements in classical, what effectively is CM+ as far as I'm concerned, are just as for measurements in quantum field theory, approximately local, but they are not point-like. This is something that is standard in the more mathematical literature on quantum field theory. So if you're willing to go with me on the idea that quantum field theory can be thought of usefully as a noisy signal analysis formalism, then I suggest that we do introduce measurements. This is a measurement theory because quantum mechanics is a measurement theory, and indeed quantum field theory is about a measurement operator value distribution which we use to construct a measurement operator which I'm going to index with something which I'm going to label F, and I'm going to click through to the next slide too soon again, where those two, in fact, I'm going to go back so that I don't distract myself, where the functions f and g, they're called test functions in the mathematical literature, they're called window functions, much more graphically, in the signal analysis literature. These also can be thought of as the README functions. If you're a computer programmer, you need to know how you got the data in computer memory that the measurement gave you. So, those describe where and when and how big, what shape, and anything else the experimenter is going to need, strictly speaking, ought to be in that description. So, now formally, in quantum field theory, an F measurement and a G measurement, which is how I term them, if those are space-like or causally separated, then they're compatible operators, in which case this expression, get the right button, is a correlation coefficient. It's just as you'd expect in classical statistics, classical probability theory. But if they are time-like or light-like separated, then they are incompatible, and this construction has an imaginary component, which I suggest we can think of as a bookkeeping, from an engineering point of view, a bookkeeping for the consequences of quantum noise for this particular pair of measurements. Now, we do have to work with causal correlations at time-like separation. We have to have models for that. What we use for that is the collapse of the wave function. It's just a mathematics for constructing a joint probability, for constructing correlation coefficients. This is obviously a way of, well, I term it in the third of the papers I cited at the top, a construction of a joint probability construction. And this is a way of rethinking the measurement problem, I find. And some people have also thought so. So what I think quantum field theory does is it, sorry, for this CM plus electromagnetism, it's empirically equivalent to, because it's isomorphic to quantized electromagnetism, the F measurement and the G measurement are always compatible. So you haven't got the quantum field theory yet, but you use the Poisson bracket to introduce the transformation algebra and use it in a general enough way that it gives you all of the operators you'd expect in quantum field theory. And you can do it. It's isomorphic. Well, it's published anyway. So finally, I think we can think of this as quantum field theory folding into the formalism just the quantum noise aspect of causality. This is something that's reasonable to do, but it's also something you don't necessarily have to do. You can make a conventional choice of using CM plus EM if that's more helpful, if it's good to keep your quantum noise separate. Okay, so 6 months ago, because of machine learning and causal modeling, and because of Frankie, damn it, I really started to wonder whether physics really needs to be about more than probability. Because machine learning, it seemed to me, doesn't necessarily try to classify data into reference classes. It doesn't necessarily count anything. So a machine learning algorithm just takes a data item in its initial state and constructs a state after that, and that need not be any kind of linearity or guided by probability distribution, probability theory at all. So relative frequency is just not part of this whole thing. And on the other hand, there are certainly generative large language models typically are constrained to be consistent with probability. It makes them much more understandable, and that's part, I think, of why people have adopted an interest in them, because they feel that it can be understood at some level. So if an algorithm is consistent with probability, I suppose we might call it Bayesian machine learning, because it does try to keep, does make it more understandable. But I do wonder whether it's better, it might be better to keep very clear in one's mind as to whether you want to go that way or the other way. I'm not saying you shouldn't go one way or the other, just it is something to keep in mind. Okay, so I'm going to go back for a moment to the data we had before. This is out 100 nanoseconds each way instead of 3 nanoseconds each way. You can see that in the center is the narrow coincidences, beautifully engineered. I mean, getting that to work, years of research, years of constructing the experiment. But you can see there's also this other broader band at around about plus or minus 20 nanoseconds. Gregor didn't know that was there. If he had, he would have had to spend an extra, well, he might have taken a day to realize what it was, but he might have spent 2 years more figuring out what the hell was causing that. Excuse my French. So there's something about debugging the apparatus that would require him to go back in and say, what could be causing this problem? What do I have to change to make the problem smaller or larger? If I can figure out how to make it larger, I probably can just say, change the direction somehow. This is something that really, debugging is very causal in this sense, but also I'm saying it can be addressed classically, so long as you're willing to put into this Planck's constant very seriously and model it as a classical Lorentz invariant noise. Mathematically, isomorphisms really make me think, like, I don't have to do the same thing for every experiment. I can just say isomorphism to you. Of course, there will be exceptions, I have no doubt. And there's another thing that I would like to know about this experiment, and that is this 10-second period that he collected data for. Yes, lots of data, beautiful. It's practically at equilibrium in the sense of it being time translation invariant in a coarse-grained way. It's not time translation invariant if you just look at this particular event here, because that is a signal going bang, not in equilibrium at all at fine-grained scale. But this is still thermodynamics. A gas doesn't have equilibrium at the 10 to the minus 9 meter scale. So here, you turn on the power. There are very few events at the beginning. You think to yourself, well, what will happen here? Will the violation of Bell inequality precede the events actually happening somehow? Will it happen later? How fast will it be? Will this time period, from lots of events to lots of events coincidence in green and yellow, will that be enough time for light to go backwards and forwards 50 times? Or will it be enough time for the light to go back and forwards 0.1 times? There's a big difference between those two things. Huge difference, and yet this doesn't probe that at all. Again, you need to have the same apparatus as he's got, or something very similar, and you need to be probing this aspect of this. Now, I've just talked about this turning on the power and off, but of course, any modulation will do, and you would like to try different modulations, see what kinds of nonlinearity there are. So if there is serious nonlinearity, you may find that the Bell inequality is satisfied very much faster or slower. So this is all, well. Okay, last slide. It does seem to me that if the world's always changing, so when Gregor finished his PhD, he went away, that laboratory space, that apparatus was gone as soon as possible. In comes a new student, uses the same optical table, and constructs their thing. So anything longer than 5 years is not going to happen. If you want 2,000 years of data, well, you can't get that even in cosmology. So there's this interplay between intervention and measurement results. It seems to me much more interactive. The debugging process could be described formally, but we don't. And I'm not saying we must, but it does seem to me that one could say, well, quantum mechanics is not empirically adequate. You cannot describe this decision and game theoretic aspect of what we're doing. And the final thing, measurement incompatibility and Planck's constant can be classical as well as quantum. So this is just to say, if you want to do causal modeling absolutely classically, so long as, when it's necessary, you put in a good Lorentz invariant description with Planck's constants and the amplitude of the noise, then you can model everything classically. Now, I'm not saying anything of this doesn't change quantum computing at all, for example. You have your apparatus, you have Gregor's experiment. He designs the experiment, he puts it all together, he runs it. The data doesn't care how I describe it. If I use CM plus or quantum electromagnetics, it doesn't matter. What does matter is the theory guides what you think is going to be an interesting experiment to construct. There's an element of the human will at the scale of design and implementation of the apparatus. There is none of my will or Gregor Reese's will is involved at the 25 kilohertz, 40 kilohertz scale of each individual event in there. The reason those events happen is because you've used an avalanche photodiode, which you deliberately used, because it exhibits events. You do not use rocks. Rocks just, well, you know, unless of course you have some really sophisticated data analysis out of the rock. And you use a very specific kind of rock, which is just as specific as the materials you use for the avalanche photodiode. I'm 25 and a half minutes in. Thank you.
Thank you so much, Peter.
Wow.
It was very, very interesting. Another fly in the ointment.
No, taking a fly out.
So, any questions before we open up the floor for our close?
Peter, thank you. That was really interesting, and I might have missed it, so maybe I'm really collapsing things much too far. But for your last point here about quantum noise and its consequences being modeled classically, is that because what matters to the dynamics of the object we already chose to treat classically is because those dynamics are sensitive to things like two-point functions of quantum fluctuations, which we can then, presumably at least under many conditions, replace with a corresponding classical object? Or is that missing more of the structure that you had in mind? I'm wondering, this last part in particular, we do that all the time as a convenience when trying to model things on, admittedly, classical computers. Yes. We'll initialize a simulation by matching the statistics of two-point correlation functions, even though we're going to then evolve them perfectly classically, but we think they had, in some sense, capturing a kind of quantum mechanical boundary condition, something like that. Is there more than that, or is that a reasonable analogy?
There is.
Okay.
The way I think about this is, for one thing, correlations at space-like separation you can consider classically because the operators do commute. At time-like separation, they don't commute, but we still have correlations we need to model. So the way we model that is use collapse. But as far as the classical physics is concerned, it's just you use commuting operators to model that. So in the signal analysis sort of framework, it's really quite natural to do that. But the analyticity I mentioned on the second slide is critical to whether you want to use the mathematics of quantum field theory or not, because analyticity is mathematically so beautiful. You don't want to throw that away at all. But on the other hand, if you're doing signal analysis, maybe the cost of having 100 million collapses in the just in the model might overturn the advantage of using analyticity.
A quick follow-up?
Yeah.
For that was very helpful, even just the gesture, right? And I
it's
wonder,
not a Wick rotation.
No, I won't even make the joke. But for that, have you already thought about things like the Legge-Garg inequality, which, as you may know, is a Bell-like inequality, but for correlations of measurements on a single system over time? It sounds like that might be a way to break what otherwise looks like an isomorphism, but you might have thought about all that as well.
I'm just going to say to you, but it's isomorphic, so anything that quantum field theory can model can be modeled by a different model, or what looks like a different model. But really, the isomorphism is completely non-local because it is a projection to positive frequency. And so it just, in some sense, it puts you in still an interpretive mess, as far as but nonetheless, it's just an alternative. It's a different way of looking at it, and it's significantly different, I think. And like I said on the first slide, in the pale gray, this, I think, does give a way to rethink renormalization as well as rethink the measurement theory.
Thanks. Chris, and then...
Or just that you had this broader band.
Oh,
you called it an artifact. So I was just wondering, you know that it's an artifact or you assume it's an artifact?
Well, I call it an artifact because, partly because Gregor didn't know it existed before I pointed it out to him 10 years ago. But it's not clear to me what the explanation for it is. If I knew what the explanation was, then I perhaps would be properly justified calling it an artifact.
No, this is the only thing I noticed from the talk.
Oh, right.
But I know that
chemistry, what's artifact for one could be found 20 years by another. Oh, this is actually the real thing.
Oh, it
Most
might
interesting
be
part.
that this indeed is completely new physics and it will transform everything. But it's more likely that it's an artifact.
Chris?
Yeah, so very curious. I know you didn't have a chance to go into a lot of the details, but I was curious about exactly what the isomorphic structures are that you're. So if they're both just Hilbert spaces, there's one sense in which it's could be trivial, but there might be more structures on the Hilbert space that you're mapping into another. And similar to Dave's question, I was wondering, just like think of the standard properties you think of the quantum vacuum, like the Riesz-Leiter theorem. How is that modeled in CM+?
What you can do is if you construct the the electromagnetic quantum field theory in terms of creation and annihilation operators, then there's an involution that you can construct which allows you to construct in terms of the same creation and annihilation operators an operator that commutes everywhere. So instead of the F measurement and the G measurement, the commutator being a function of the F and G, a linear function of the F and G, instead of that, you find that the commutator of this new F measurement and G measurement is 0. So the involution does the job, but the involution has a time reversal in it, and that's non-local. So it's a very, very simple construction. If I was giving an hour-long talk, then it would be in there, and in one slide. It's quite simple. But anyway.
Did you have a quick follow-up?
So I still don't understand how the entanglement properties of the quantum vacuum would be mapped into the way you're describing the quantum effects due to the classical noise.
Well, you now have this new mathematics, and you will be free to interpret it in whichever way you like. Now, negative frequencies, of course, could be interpreted as retrocausality. But on the other hand, it doesn't necessarily have to be interpreted that way. Just as there's different interpretations you can have of the quantum mechanics mathematics, you can have different interpretations in this sort of way. It's a free-for-all.
Okay, great. Thank you so much, Peter.
Thank you.
Okay.